Hello guys, and welcome back to the GCE Maths panel online. This is the last lesson of chapter 7, which is on limits and continuity. In this particular lesson, we are focusing on L'Hopital's rule and indeterminate forms. This lesson is very, very important with a lot of tricks and so many past questions and examples in it. And I implore your indulgence to make sure you watch these questions to the end. Another thing that has been brought to our notice is that most of you watch these videos, but you have not subscribed at all, which is not an encouragement. And because of that, the panel has put in place a mechanism such that if you have not subscribed, you cannot continue to watch the videos. You actually need to subscribe to be able to continue to watch the videos. And note that subscribe, you are not supposed to pay anything. Subscribe is free. It's just that whenever a video is uploaded, you are notified. When you subscribe, you turn on the notifications. So our focus in this video is limits, indeterminate forms, and L'Hopital's rule, as well as so many different algebraic tricks. Please make sure you love this video, you like this video, you leave your comments, you share this video to the different WhatsApp groups in which you find yourselves as a sort of motivation to this panel. Now, let us consider this particular function. Suppose we are trying to analyze the behavior of this function. Although f is not defined when x is equal to 1, we need to know how f behaves near 1. If you look for the limit here as x tends to 1, it is going to be 0 on infinity, right? So this function is not actually really defined. So in particular, I would like to know the value of the limit as x tends to 1. We would like to know the value of this limit as x tends to 1. So in computing limit, you can apply law 5 of limits, but that is not really going to make sense. In fact, though the limit expression 1 exists, its value is not obvious because both numerator and denominator approach 0. And this is not defined, right? If you look very well, the limit here is you have 0 over 0 now. So this is one of the indeterminate forms in which find where we have 0 over 0. And we are trying to see what we do here. Normally, with this type of limit, we apply L'Hopital's rule, which shows that in general, if we have the limits of the form, the limit of f of x on g of x as x tends to a, giving us a value of the type 0 over 0, for example, then this form is an indeterminate form. So for rational functions, we can cancel common denominators. For example, let's look at this limit. As x tends to 1, if you put the value 0, we have 1 minus 1, which is 0, over 1 minus 1, which is 0. But we can factorize and simplify. This will give us x into x minus 1. All this over this is the difference of two squares. You have x plus 1 into x minus 1. So these two can cancel out. When they cancel out, you'll be left with x over x plus 1. And as x tends to 1, the limit here is a half. This is using the algebraic trick, which we have used before. So this is the limit for this function. We can equally use the geometric arguments to show this. We have used this one before, the algebraic tricks. The limit as x tends to 0 of sine x on x is equal to 1. So let us see. Another situation of a limit is this other one. We have just discussed this one. As x tends to infinity, we will have infinity over infinity in this case, right? This one is going to give us infinity over infinity. So there is a struggle normally between these two, with the cases where you have 0 over 0 and the case where you have infinity on infinity. So in general too, if the limit of f of x on g of x as x tends to a gives us a function of the type infinity over infinity, then this limit does not exist and we equally have an indeterminate form of the type infinity on infinity. So let's look for the instance. We have this particular case as x tends to infinity. Normally, as we saw in rational limits, we can take highest divided by highest. We still have a half here, right? We still have a half here. So this is an example of what we have done. We are still introducing the infinity over infinity types and the 0 on 0 types. So this method, though, does not work for limits such as the expression we have just previously seen. L'Hopital's rule is applied for indeterminate forms. So let us suppose, for example, f and g are differentiable functions on the open interval given. If the limit as x tends to a of f of x is 0 and the limit of g of x as x tends to a is also 0, And the limit as x tends to a of f of x is positive for negative infinity, and g of x is also positive for negative infinity. And we end up with the type 0 over 0 or infinity over infinity, then we can apply L'Hopital's rule as follows. This limit can now be written as the limit of f of x on g of x as x tends to a. In the case where we had 0 over 0 or infinity over infinity, should be equal to the limit of f prime of x on g prime of x if the limit on the right exists. Okay. Maybe this will not be very clear to you, but L'Hopital rule says that when the limit of a quotient function is equal to the limit of the quotient derivative, provided that the given conditions are satisfied. This is what L'Hopital's rules tells us. So the limit of a function that gives us the form infinity over infinity or 0 over 0 is equal to the limit of the derivative of the numerator over the limit of the derivative of the denominator, provided the denominator limit is not equal to 0. That's in simple terms now. So the rule is valid for one-sided limits and for limits at infinity or negative infinity. So you can apply these limits at all of these points. And this is normally a proof of L'Hopital's rule. Okay, but they will not ask this in the GCE. They will not ask this. The limit of as x tends to a of f prime of x on g prime of x is the same as this. You can see right at the end. So this is where L'Hopital's rule comes in. Now let's look, for example, this function. I want to look for the limits as x tends to 1 using L'Hopital's rule, right? So differentiate the numerator. We differentiate the numerator, we'll have 1 over x. We differentiate the denominator, we'll have 1. We now apply the limit. The limit of this function is equal to 1. That is using L'Hopital's rule. The limit of this is equal to the derivative of the numerator over the derivative of the denominator, and we take the limit. And this gives us 1 as the answer. All right, now let's calculate this other limit as x tends to infinity. If you just put infinity, you have infinity over infinity, right? So in this case, we still apply L'Hopital's rule, but just by observation, we can equally still take infinity for the numerator and infinity for the denominator. So let's apply L'Hopital's rule here and see what we have. When we differentiate the numerator, we'll have e to the x still. If you differentiate the denominator, you have 2x. If you substitute infinity, you still have infinity over infinity, right? So it therefore means that we can continue. In this case now, we still differentiate the numerator again, we'll have e to the x. And differentiate the denominator, we'll have 2. We will now apply the limit here, we'll have infinity. Because I have infinity divided by 2 now, which is in positive infinity. Okay? Yeah. Now, what about this other limit? At infinity, we'll have infinity over infinity, so we can use L'Hopital's rule. We differentiate the numerator, we'll have 1 over x. We differentiate the denominator, we will have 1/3 x to the power minus 2 on 3. Chapter 8 is on differentiation. We'll visit most of this in chapter 8, okay? Yeah, we're supposed to take this after chapter 8, but let's just take it here. So take this after chapter 8. So at this point, is that we will still have the limit on the right left is now determinate. So you still have, if you put infinity here, you have, let me see, you have 1 over infinity. You have the type 0 over 0 here. If you look at this type, 1 over infinity is 0, right? The denominator now. This minus 2 on 3, we can put this thing now as 1 over that. That will give us 1 over infinity, which is still 0. This will give us the type 0 over 0. So what do we do now? We still differentiate again. When we differentiate again, this is what we are going to obtain. We'll have 3 over the cube root of x. So as x tends to infinity, we'll have 3 over infinity, which is 0. This limit now becomes equal to 0. Okay. Now let's look at this other limit, tan x minus x on x cubed as x tends to 0. Tan 0 is 0. So 0 minus 0 is 0. All that over 0 is 0. So this gives us 0 over 0. So we can differentiate now. When we differentiate tan x, we have sec squared x. We differentiate x, we'll have 1. When we differentiate x cubed, we have 3x squared. If we fit zeros here now, what do we have? So have 0 for the denominator, and what is sec 0? So now sec 0 is 1. 1 minus 1 is 0. So we'll have 0 over 0 still. So we can still differentiate this one. We'll have 2 sec squared x tan x on this. When we put the value now of 0, what are we going to have? Sec 0 is 1 and tan 0 is 0. So we still have 0 over 0, right? So we still differentiate. We differentiate again. We will end up with these two limits, or we can separate like this. We can separate it out. You have the limit of sec squared x as x tends to 0 times the limit of tan x on x as x tends to 0. Now this limit tan x on x as x tends to 0 is 1, and sec x as x tends to 0 is 1. So 1 times 1 times 1/3 gives us 1/3. Are we together? That's why this limit here is equal to 1/3, because tan x on x as x tends to 0 is 1, and sec x squared on 1 as x tends to 0 is also 1. So 1 times 1 times 1/3 is 1/3. You can watch this one many times, okay? The writings are many, but the explanation is short. What about these other limits as x tends to pi from below? So sine pi is 0, because pi is, what do we have? So that gives us that. So is this, we can differentiate. We differentiate sine x, we have cos x. Differentiate cos x, we have sine x. And this will give us cos x on sine x, which is cot x. And as x tends to pi, cot x tends to negative infinity. Okay? In trigonometry, you understand this better. This is wrong. Although the numerator sine x tends to 0 as this tends to this, notice that the numerator 1 minus cos x does not approach 0. So the rule can't be applied. Let's see what we do here. So as we mentioned before, this limit as x tends to pi, we have sine pi, which is 0, and cos pi. Cos pi is minus 1, right? 1 minus minus 1 is 2, 0 on 2. So here we don't need L'Hopital's rule. We just need to apply the limits directly. And our limit here is 0 on 2, which is equal to 0. So take note of this. This is a trap. This is a trap. Because cos pi is equal to what number? Yes, it's -1, and sine pi is 0. That gives us negative infinity. We have to be very, very careful with this rule, okay? So we should not blindly use the L'Hopital's rule. That is the emphasis here. Do not blindly use the L'Hopital's rule. Do not. Because if you look here very well, you can apply this directly and you have the answer. You have the limit. The limit here exists. Don't blindly use the L'Hopital's rule. Thank you. Okay. So when you are evaluating any limits, you should consider other methods before using L'Hopital's. L'Hopital should be your last resort. You should have considered all the other methods to come to L'Hopital's rule. And if the limit of f of x of x tends to a is 0, and limit of g of x tends to a is infinity or negative infinity, then it isn't clear what the value of this product is. It isn't clear because 0 times infinity or negative infinity, you are not clear of what you're going to have. So you can struggle. But this is another thing that we can do. We can write the limit of this form f. Instead of writing fg, we can write it as g over 1 over f, such that we will end up one of these types, either 0 over 0 or infinity over infinity, so that we can now apply L'Hopital's rule. So we can bring it to this form. Whenever we have limit of the type 0 times infinity, we try to arrange the function such that we end up with something like this. Fg should be equal to g over 1 over f, right? So we can apply L'Hopital's rule. For example, let's apply this limit. limit of x ln x as x tends 0 from above. This limit is indeterminate because as x tends 0 from above, the first factor x tends to 0, whereas the second one tends to negative infinity. The ln as x tends to 0 from above is negative infinity. So what's 0 times negative infinity? Is it negative infinity or 0? So be careful with this type of limit. We have to see how we can arrange it and not just blindly apply L'Hopital's rule. So writing x, you can write x as 1 over x, right? And 1 over x tends to infinity as x tends to 0. So as x returns to 0 now, 1 over x returns to infinity. So here, using L'Hopital's rule, we can now write this as ln x over 1 over x now. And this will now give us, as x tends to 0, we'll have infinity over infinity. So we can apply L'Hopital's rule now at this point. We differentiate and differentiate. You have 1 over x over that. And we will now take this limit is going to be equal to 0. So in general, when we write an indeterminate product, we try to choose the option that leads to the simpler limit. Equally, this is also an indeterminate form. If the limit of f is infinity and limit of g is infinity, and we end up the limit of infinity minus infinity, this infinity minus infinity is also an indeterminate form because you don't know that infinity minus infinity is 0 or what. 0 times infinity or 0 times negative infinity is indeterminate. Infinity minus infinity is indeterminate. Infinity to the power infinity is indeterminate. 0 over 0 is indeterminate. Infinity over infinity is indeterminate. So again here, there is a contest between f and g, and we need to know who wins. So we try to make sure that we can make it to be of the form 0 over 0 or infinity over infinity so that we can apply L'Hopital's rule. Okay, so we try to see if we can convert the difference into a quotient so we can apply L'Hopital's rule. For example, let's compute this limit. This one is a higher limit, mostly for further maths and high school. But with this one, we can write this one of this form. Can you see? Yeah, we can write it in this form. Now we have a common denominator cos x. We can now apply this limit, but it's going to give us some sort of infinity over infinity or 0 over 0. Because we know that pi on 2 is 0. And we have 1 minus 1. That's 0 over 0 now. So we can now apply L'Hopital's at this point because sine pi onto that sine 90 is 1. 1 minus 1 gives us 0 over cos 0. Cos 90, which is 0. So we can now differentiate numerator and differentiate denominator. And this is what we have now. So we can now have cot x as x tends to 90. And that is cos 90. What is cos 90? Cos 90 is 0. Sine 90 is 1. 0 over 1 is 0. So this is what we do for this rule. So note that the use of L'Hopital's rule is justified now in this particular case. So you equally have other indeterminate forms like this. You can have the type 0 to the power 0, infinity to the power 0, and 1 to the power infinity. Each of these three cases can be treated in two ways. You can use natural logarithm, or can you write the function as an exponential. Now let's look at this particular limit. Calculate this limit as this limit. So cot 0, what is cot 0? It's undefined, right? Sine 0 is equal to, good. So you start, first notice that as x tends to 0, you have 1 plus sine 4x, this tends to 1. And cot x will be equal to infinity. So you have 1 to the power infinity. This is an indeterminate form. We can do this one by taking ln on both sides first. Ln y will be equal to cot x ln that. The next step now, the limit of ln y as x tends to 0 should be equal to the limit of the right hand side also as x tends to 0. So this gives us the limit of 1 plus sine 4x on tan 4x, because that is cot 4x. Cot x is as 1 on tan x now. So as x tends to 0 here, what do we have? Ln 1 sine 0 is 0, 0 plus 1, 1, ln 1 is 0. And what is times 0 is 0. So we have the type 0 over 0 here. We differentiate numerator and denominator and apply limits, and we will end with 4. So the limit of ln y as x tends to 0 is equal to 4. At this step, we now use this idea. Since this limit is equal to 4, what does it mean? So from here now, we can now look for y, right? Yes, by raising both sides to the power e. Because look at ln y, the limit as ln y as y tends to 0 is equal to 4. Can you see? We now raise both sides to e, as we have done here. And that will give us the limits of that function as x tends to 0. Okay. What about this other limit? This one is also indeterminate now. We have 0 to the power 0. We have 0 to the power 0. So what do we do? So x can be written as e to the x to the power x now. Convert to exponential form. And the limit here will end up giving us 1. The limit will end up giving us 1. X tends to 0. We have 0 times ln 0. So we have 0 times this. We have e to the power 0, which is equal to 1. Guys, please make sure that you join us for chapter 8. And if you don't understand anything in this tutorial, please watch it over again. And if you still have a problem, you can leave a comment in the link below. Thank you so much. For you to watch the next chapter, you have to subscribe and share this video to watch the next chapter. Otherwise, it will not be possible. Thank you so much for spending your time, for staying with us, and see you in chapter 8, which is differentiation. Bye-bye.